In case you hadn't noticed yet, I have not my old computer back, but one that's pretty close to the same as it. They cloned my hard drive onto this one, so it acts just like the other one. Seems like it might be a little slower, but at least it's not as bad as the last one was, nor the ones from the library. Library, I couldn't record anything. So since we didn't record, I don't think last time, and sorry about that, anyone who missed the lab, you have to just get with someone and get it caught up, or get with me and get it caught up. Let's go over where we are. First, normally on Fridays I have office hours on the Birmingham campus, 7:45 to 11:45. Okay? Tomorrow I've got to go get my tag changed for my new car, and I was going to do it after work. My wife said, "You don't want to do that. You'll be there all day. You need to get there first thing in the morning." So I checked with my boss yesterday, and he said, "Oh, by all means, do it first thing in the morning. You'll get back here at a reasonable time." So I don't know what time I'll get to the Birmingham campus. I don't think it'll be any earlier than 9, if even possible to be 9. But it could be 9:30-ish or so. Maybe as late as 10, I hope not. But I'll just go 4 hours from whenever I get there until I leave. I'll be there at least 4 hours. Okay, so that's tomorrow. All right. Of course, you know, next week, no classes. Sorry about that. If you do need to take care of any business with the college, the business offices will be open. All the offices will be open Monday, Tuesday, and at least through Wednesday morning. Okay? If you need to talk with an instructor, an advisor, we're going to be in professional meetings here on the Birmingham campus. We won't be over here on Bessemer, on Birmingham campus. And we'll be there Monday and Tuesday, so it's going to be hard to reach us on Monday and Tuesday. Wednesday, we will be back in our offices. Okay, so you can catch us then for those folks who didn't go to Montgomery. Now, some people, a lot of administrators and a few instructors and maybe a few staff people are going to Montgomery Sunday, Monday, and Tuesday. And so if they go Sunday, they probably won't be back on Wednesday. But if they only go for Monday and Tuesday, then they'll probably be in the offices on Wednesday, or they could be. Now, let me say this, too. A lot of people will choose to take personal leave on Wednesday rather than coming back here, coming back to the offices. So you might not be able to catch someone. If you need to talk with somebody next week, set it up this week, find out what days, times, place they'll be available, and then plan from there. Don't just show up. You might not find them. Okay? Okay, so that will be next week. I will be on campus, this campus, Wednesday, and typically the day before Thanksgiving, they usually let people go home early. It's not guaranteed. I've heard that some years they've done it as early as 12. Last year it seems like it was around 2. And they may not do it at all. Okay, so it may be, and like I said, a lot of people will take personal leave rather than sitting around letting the turkey not cook, you know. So anyway, they'll you need to check with people before you come to campus because you may not find them. But don't plan to go to any office or anything after noon on Wednesday. People will start disappearing or we'll all be gone if they let us go. So try to take care of any business you have Monday, Tuesday, or Wednesday, or if you need to see an advisor or instructor, try to arrange for them, you know, to meet them on Birmingham campus Monday or Tuesday whenever we won't be in meetings, or wherever you're going to meet them on Wednesday, but make it in the morning, because the odds are people will start disappearing. Okay, another issue. They have open student course evaluations. Have y'all seen them yet? Okay, got them done already?
Yes.
Fantastic. How long did it take?
2 seconds. 30 seconds.
Okay, it should be a little more than 30 seconds, but okay. 5 minutes? Okay. No, not a big sweat, so please do them. Please do them. Don't, if you want to wait until you see what your final grades are, that's fine. You can do that, but don't forget to go back and do the student course evaluations, okay? I know when I was an undergraduate and when the end of the term came and I finished my finals, I was so, sometimes so wiped out, I wouldn't have thought of going back and doing an evaluation. Back then, we did them in class, before you left, so it wasn't on the computer. So please don't forget to do your student course evaluations. Okay, you can do them now if you want to. Probably not that much will change, but if you do want to wait, you can do that too. All right, let's talk about where we are. We're in radiation. We've got section 4.4 to go after we do this, and then 4.5 thermodynamics, and that will be it for the chapter. So I'm pretty sure we'll finish this in the 2.5 hours or whatever we got left of that now. And we'll probably have time to get started on chapter 6. We're not doing chapter 5. We're moving from 4 to 6. Okay? Now, let me get this set up. Since we're finishing chapter 4 today, we will have our last lab on chapter 4 today, the second lab. That will be from 5:45 to 7:45. I don't think it'll take anyone that long. It's not a super short lab. The trouble is this lab takes longer to set up than any other lab. So as soon as I let you go, then I'll be rushing around trying to get the lab set up because I'm dealing with hot waters and cold waters and ice and stuff, and you can't set it up beforehand. I've got everything in there, but I couldn't set up the things until the lab actually going to begin. Now, and I think we will finish the chapter today, that means the test will be Tuesday when we get back from Thanksgiving. All right? That'll be the last 30 minutes then. If we get enough covered today and Tuesday in chapter 6, we'll probably be ready for the first lab Tuesday as well. So we'll do probably 2 hours of class, 2 hours of lab, 30 minutes of test on Tuesday. If we get far enough today and Thursday.
So no test today?
No test today, because we didn't finish the chapter today. Okay? So we'll just do, class until 5:45 and lab after that. Yes? Okay. When we go to the lab, I'll give it to you. Is that okay?
Yeah.
Okay. All right. Okay. Now, we have, once we get back from Thanksgiving, 2 more weeks of class, and then during finals week, we also have class on the Tuesday, and then have the final on the Thursday. Okay? Now, we'll see how things are going when we get that far. Once we finish that last class on Tuesday, which will probably have a lab in it, I'm guessing, that's too far off to tell, then any time after that you want to take the final, you can. You don't have to wait till Thursday if you want to get home to Mama. So we can, we can work that out as we get closer. But we do have class today, 2 weeks after that, so that's 4 more classes, and then the Tuesday of finals week, and then the final will be the Thursday of finals week, or sooner if you want to take it sooner. Okay? Any questions? All right. Last time we were talking about methods of heat transfer. What were the first 2?
Friction, methods of friction.
No, of heat transfer.
Oh.
The first one is mostly in solids. Heat is transferred by everybody was paying close attention, I could tell. Okay. What was the mostly by contact? It had to be by contact. What is that? Flip your page over 1 page and you'll see the title in blue. Conduction. Very good. Conduction. The second method of heat transfer was mostly in fluids, which is liquids and gases. And what would that be? Convection. Very good. Okay. The third method is one we're doing now, and that's radiation. Radiant energy is the energy associated with electromagnetic waves. Okay? Now that includes light, that includes X-rays, that includes heat, That includes, when I say heat, infrared rays, ultraviolet rays, cosmic rays, radio waves, you name it. That's radiation associated with electromagnetic waves. It can and best operates through a vacuum. Conduction can't happen in a vacuum. Convection can't happen in a vacuum. Radiation is the only one that can happen in a vacuum. In fact, that's where it happens its best. It will go through a material such as air. Radiation will move through air fairly easily, but then through other things a lot more slowly and more difficult. Okay? Now, all objects emit and absorb radiation. All objects. In fact, usually your good absorbers are also your good radiators. Okay? All objects emit and absorb radiation. The temperature determines three things. First, the emission rate. The higher the temperature, the more rapidly a body, an object, emits radiation. So the hottest stars emit the most radiation. The coolest stars emit less radiation, but still emit quite a bit. And then very cool objects hardly emit any radiation at all. So temperature determines the emission rate, the rate at which, time rate of emission. Okay? The intensity of the emitted light, the temperature also determines that. Melva can recall. Thank you. Yeah, thanks. Okay. And Physical Science 111 that you took in the first mini term, the hottest stars are typically what color? No, actually red is the coolest stars. Bluish, the whitest, yeah. The blue stars are the very hottest. The whitest are the next hot. Then you get the yellow stars, which guess what ours is? A middle-of-the-road yellow star. Medium amount of temperature and medium rays of emitted light. And then the cooler stars are the oranger and the red stars. Okay, in fact, the red giants are on their way out. Okay, so the intensity of the emitted light and the type of radiation given off, the higher the energy, the higher the temperature, the more high energy radiation is given off. Okay, temperature determined determined by the balance between the rates of emission and absorption. Okay, now an object. Okay, let's take your car right now. Okay, sitting out there. Anyone leave the window cracked today? Of your car, of your vehicle? No, probably not. It was sort of cool this morning. I didn't leave mine either. Okay, but if you were to go and open the car door right now, it would feel warmer or cooler than it is outside.
Warmer.
Big time. Okay. And that's because it's been absorbing radiation at a greater rate than it's emitting radiation. Okay? The reason for that is glass. Okay? The other example of that is global warming. We are far enough from the sun that we shouldn't support life too well. Okay? But we do. And the reason for that is we have this nice warm blanket called an atmosphere around our planet. And that atmosphere does two very good things for us. The first thing it does, thank you very much, it doesn't let the harmful radiation in. Some of this very high energy radiation, the gamma rays, X-rays, a lot of those cosmic rays, they are blocked from entering our atmosphere. Thank you very much. If they came in, we'd be dead. Okay? We die of radiation poisoning. Speaking of which, here is Adam. No, I'm sorry, I didn't say that. Okay. Now, the second thing our atmosphere does for us is traps the heat. Okay? Because the energy comes in. Okay? First, the outer part of our radiation, of our atmosphere, somewhere out there is a level called the ionosphere, okay? and there are other spheres out there, but the ionosphere is one of the ones that blocks the harmful radiation from coming through. Okay? But the white light does come through. Okay? It comes through, that's what lights the planet. Okay? It gets through, but then when it does come through our atmosphere, the white light lengthens in wavelength a little bit and goes from being white light to infrared radiation, which is heat. Now that radiation doesn't have enough energy to make it back out through the atmosphere. So the balance of emission, we absorb more than we emit. We are always emitting some, we're reflecting some, but we're absorbing more than we send back. Okay? Emit. Now, some of the good absorbers in our atmosphere are carbon dioxide, methane. Your sulfur dioxide would be a good, we don't have that much of that out there, but those are the things that keep in other words, they expand the wavelength so now it doesn't go back out. Okay? Now, what the feeling is on global warming is that we are emitting way more carbon dioxide. These things have been measured. Way more carbon dioxide than what the planet used to have in the atmosphere, mostly because of our burning of fossil fuels. It started, you could see the trend back when the Industrial Revolution really got into play, and we started heating up things, burning stuff as fast as we could, and since then carbon dioxide levels, they're going up really, really fast. Now, hopefully today with some of the activities we're doing, they're leveling off and maybe start coming down some. Well, I hope so. Otherwise, we could be in pretty serious trouble. Now, there's a lot of people, or a few people, who say, I don't believe any of this. It's all natural, blah, blah, blah. If you look at the data, the vast majority, I think so, I've seen the figure like 97% of the scientists who study it come to an agreement, yeah, we're contributing to global warming. But the people who don't want to believe it, they quote the 3% like they were the top people in the world. Okay, so they say there's disagreement. Well, there's some disagreement on how fast it's happening, what degree it's happening, and stuff like this. But like 97% of the scientists who study it say, yes, it is happening. The data are really irrefutable almost. I mean, they're so clear. And the models they developed years ago for it, everything's matching it better than any other models they've done before. It really seems like it is. So that's the temperature balance. The temperature is determined by the balance between rates of emission and absorption. With all the extra carbon in the atmosphere, we are absorbing faster than we're emitting. Therefore, our temperatures are going up. Our ice caps and sheets are melting. Okay, we have more violent hurricanes and other storms, and they're at a higher level than we used to have on average, on balance. So that's radiation. Now we start 4.4. Energy, heat, and molecular theory. Frankly, I don't know what it seems like to you, but it seems like we've been over this several different ways, and we're still going to do it. There are two responses of matter to heat. Okay? What are these? Well, of course, you heat something up and the temperature goes up. Temperature increases within a given phase. So if you're heating water, the water gets to be a higher temperature. Okay? If you're heating steam, it goes to a higher temperature. If you're heating a metal, it goes to a higher temperature. The heat goes mostly into the internal kinetic energy, and the average internal kinetic energy, that's a measure of temperature, or that correlates to temperature. The heat that's involved with that, and we talked about this last time, is specific heat. That's the heat that's required to raise a certain mass of a certain material, a certain temperature, a certain temperature. That's specific heat. Okay? Calories per gram degree Celsius, specific heat, or calories per kilogram, kilocalories per kilogram degree Celsius. Okay, that's specific heat. But is that the only response to matter when you heat it? Is that the only response to matter when you heat it? When you add heat to it? No. Remember in the lab last time, we had that beaker of ice sitting over there. And the room was warmer than the ice was, so the ice, was it changing temperature?
Melting.
Why not? It was melting. It was changing its phase. So the second response, here's the first response. Okay? Within a phase, like ice, you heat ice. Okay? If you heat ice, it actually warms before it melts. It actually warms before it melts. If you got water, water will warm. Okay? If you got steam, you add more energy to steam, you get a higher temperature. So if you've got solid, liquid, or gaseous phase, and you heat at that level, you're going to change its temperature. However, once the ice reaches its melting point, and then you add heat, you don't change the temperature anymore. You change the phase. Some of the ice changes to liquid ice. What you're doing there is breaking the bonds, the crystal structure that makes ice, and releasing that and making water. So while that's going on, you have no temperature change. That now is increased molecular potential energy. You're absorbing the heat, but it's breaking the bonds, not changing temperature. Same thing with ice water. Okay, as long as ice and water are present together, there is no change of temperature until all the ice melts or all the water freezes, and then you start having a change of temperature. If you're heating it up, once all the ice melts, then the temperature goes up again. But as long as ice is melting, it's at a constant temperature. The melting point of ice, the freezing point of water, it stays there until all of it changes phase. Then water, when you start to boil it, and we talked about this last time too, once you bring water to a boil, what's its temperature approximately?
212.
212 Fahrenheit or 100 Celsius. Okay? Now you add things to it like put salt in the water or something else, you'll change that slightly. Okay? And if your barometric pressure changes majorly, that'll change slightly too. But once you start boiling the water, you can add as much more heat as you want to. You're not going to raise that temperature above 212 or 100 Celsius because you're changing phase. And until all the water becomes water vapor, then it stays at that 100 degrees Celsius, 212 Fahrenheit, as long as there's liquid water and gaseous water present. Once it all evaporates, now you can start increasing the temperature of the steam. And that's what they do in power plants and things like this. You're dealing with superheated steam, very high temperature steam. They don't want any water droplets in that at all. They can destroy a turbine if you have those water droplets being fired through there. They want it all steam. Okay, that actually was more your change of phase. Okay, here we go. The second activity is a change of phase. A phase change at a constant temperature, that's related to changes of internal potential energy as opposed to internal kinetic energy. Changing internal kinetic energy raises temperature. Changing internal potential energy keeps the temperature pretty much what it was. We don't use specific heat when you're dealing with that because specific heat has a change of temperature in it. Here we use the latent heat. Okay? Let's see if they give you that formula. Well, not yet. We'll get there in a minute. Okay? Here is a diagram that indicates this pretty well. Let's say we have ice down here at minus 20 degrees Celsius. What phase is that? I gave it away when I said ice. What phase is that?
Frozen.
Yeah, okay. What do we call that phase?
Solid.
Solid. That's a solid phase. And at minus 20 degrees ice, you add some heat. Does that ice melt?
Yes.
not at minus 20. It warms without melting because you're at minus 20. It won't start melting until it reaches the melting point, which is
0 degrees Celsius.
0 degrees Celsius, 32 Fahrenheit. Then it no longer will warm. Add more heat, the temperature stays right the same. Here you add heat, the temperature increases from minus 20 to minus 19 to minus 15 to minus 12. Keeps heating, you keep warming until it reaches 0. Then you keep adding heat, no change in temperature, the ice starts melting. You're breaking down the bonds, you're changing the potential energy, internal potential energy of those bonds, and you're melting the ice until all that ice melts and it all becomes water. And then at that point, the water at 0 degrees Celsius now starts warming again because there is no more ice present, and it will warm. Now, what is the type of heat that deals with this warming of ice?
Thermal.
Okay, no, the specific, I just gave it away. The specific type of heat was specific heat. The melting, what kind of heat are you dealing with there? Latent heat. Okay. Latent is a word that means hidden. You're heating something, but you don't see a change in temperature. So you don't see where the heat's going. It's changing the phase. That's latent heat there. Okay? Then you're warming water. What kind of heat there? Specific heat. Then when the water gets up to the boiling point, which is 100 degrees Celsius on the boiling point of water, then what happens? Yes, it starts changing phase again without changing temperature. You're still adding heat, no temperature change. Temperature change all the way up to there. When you add more heat, you have a phase change. And at that point, you have water and steam in the same environment. You're only going to have. And that's why when you're cooking those beans, once you bring that water to a boil, adding more heat does nothing to make it boil faster. It doesn't cook them any faster. Put a lid on it. If you have already got a lid on it, turn the heat down. Just keep it at a boil. Won't cook just as fast. You just won't evaporate the water as rapidly. But that's all you're doing by turning up the heat. You're not changing temperature. You're just boiling it faster. Okay? But then when all that water boils away and everything becomes steam, when you add, oh, and by the way, what kind of heat is this? Latent heat again. A different latent heat from down here, but it is still latent heat. And then once it all becomes steam, you add more energy, and what happens? Change your temperature. So what kind of heat are you talking about there? Specific heat. Very good. Okay? Now, we've already talked about what those specific heats were for water and ice. So, ice, water, and steam. For ice, if I'm not mistaken, it was 0.5 grams. Yeah. Calories per gram degree Celsius. For water, liquid water, it's 1 calorie per gram degree Celsius. For steam, does anyone remember what that was? 0.48. Okay? Almost the same as ice. A little bit less than ice. Water is the highest specific heat of any other thing. Now, we'll talk about the latent heats in just a minute. Let's get the formula up here if they're going to do it. No, they didn't. So let me put the formula up here. Now, because they've gone to a dark background here, I'm going to change my pen. Okay. Oh, and I don't know, did I tell y'all? Yeah, I did. My computer's back. I am recording again. So I think the last class, there was no recording, but I will leave the recording I did the last time I taught this class out there. It won't start and stop at exactly the same place, but you'll get most of the stuff from there if you need it. Okay, what color would you like to write on this dark background?
Purple.
Purple? That's probably not going to show up too much, huh?
Teal.
I can't hear.
Teal.
Teal? I really don't see a good teal. Maybe that's closest to a teal. Okay, yellow would probably do best. You want yellow?
Sure.
Okay, let's try yellow. Okay, yellow. Yeah, here we go. Now, we call this latent heat. Remember what the symbol was for specific heat? Let's go back to that. What was the symbol for specific heat? C. Okay, that means yes in Spanish. Okay, so it's C. Let's write those down again. C for ice was 0.5, I think it was 0.50, wasn't it? It was in a table back here. Yeah, specific heat for ice was 0.500. And those units were calories per gram degrees Celsius. Okay? Specific heat for water, liquid water, was 1.00 calories per gram degrees Celsius. And the specific heat for steam was 0.48. Did that have an extra zero on it? Let me see. Steam, yeah, 480. Okay? Calories per gram degrees Celsius. Those were your specific heats. Latent heat should be a little bit easier to remember. Its symbol is an L, capital L, for latent heat. But we have two different latent heats. We have the latent heat of fusion, which you can also think of as freezing, which you can think of as melting, all the same. That latent heat for freezing, fusion, melting, for water is, and it's in your text here, on page 102, right near the bottom of the first column, the latent heat for water, the latent heat of fusion, is 80.0 calories per gram. 80.0 calories per gram. Now, what's missing in the units here that you'd had in the unit for specific heat? What were units there? Calories per gram. There was something else.
Square.
I don't know what you said.
Degrees Celsius.
Degrees Celsius. Why are we missing degrees Celsius here? There is no change of temperature in latent heat. It's all at the same temperature. So it's just calories per gram. Okay? And look, that's a pretty good sized number. Okay? Big numbers for specific heat was 1, 0.5, 0.48. Those are the largest numbers in our table. Latent heat, 80 calories per gram. That's a lot of heat to melt or to freeze water. The other latent heat is latent heat of vaporization. Now, this is the same as the latent heat of condensation, which is when you're removing heat, but we always call it L sub V. And does anyone know what that one is? If you look at the right-hand column near the bottom of the page is 540.0. 540.0 calories per gram. You talk about some heat. That's a lot of heat to evaporate water or given off when you condense water. Okay? Freezing water is a lot. Evaporating water is way more. And that's why, what does our body do to keep you from overheating?
Sweat.
Yes, and for every gram of water you sweat, you perspire, that evaporates, you're losing 540 calories of heat. That's exactly what it's designed to do. Now, we had an English instructor here a few years ago. She retired, but she had some sort of a malfunction in her metabolism. She could not sweat. So she would overheat at the drop of a hat almost. She was red-headed and red-faced, and as she got too hot, her face became beet red. She just could not get rid of the heat fast enough. So her English classroom was an icebox down there. She couldn't sweat, so she had to have it so she could teach. And people just wore their coats, all year long. They had their coats in that classroom.
Did she tell her students why?
What's that?
Did she tell her students why the room was so cold?
Oh, of course, yeah,
Okay.
yeah. And they understood. Okay. There's a lot of now. This also leads to. Did any of you play sports? I know some of you probably did. Okay. On very hot days in the summertime, what did they worry about?
Somebody passing out.
Okay, and why was that?
Overeating.
Overheating, and why was that? The hot days, that's understandable, but what made it work? Okay, that was part of it, but actually more than that is that if you had high humidity, then your sweat wouldn't evaporate. And you count on the evaporation to cool you off. And if you had a high humidity and you weren't evaporating sweat, you can easily go into heat stroke or heat distress. And that's why at some football games and football practices in the fall down here, we went to a couple when my niece was a cheerleader, and I swear it was early in the season, still very warm. The officials would call timeout, and we'd sit there. The football players would go over, and they'd have to cool off some because they were so afraid the students would have heat stroke.
About the official timeout.
What's that?
The official timeout.
Yes, official timeout.
It just started those a couple of years ago.
Yeah, I know. It hasn't been long. That may have been one of the first years they did it. And boy, it made the game so much longer. Already hot out there, and then you had all those breaks. But it was for the good of the students. Now, the formula. Does anyone remember the formula or the equation we used for specific heat? We used it repeatedly, so y'all remember it. What is the symbol we use for heat? Did someone say something? Symbol for heat?
Q.
Q is equal to MC delta T. And that's why C had units of calories, that's for Q, per gram, that's the mass, per degree Celsius, that's the change of temperature. So yeah, that made sense. Guess what the formula is for latent heat? Pretty similar. Guess what you're talking about? Heat, so it's Q is equal to M L blank. The L could be LF or LF or LB. QML. And then your subscript depending on which one you're talking about. Notice you don't have a delta T here because for latent heat there is no change of temperature. So calories per gram. That gives you your unit there. Okay? There's the formula. It's on page 102 near the bottom of the second column. Okay. There is a figure 419 in the text. It isn't showing up on the slides. It's talking about work done against gravity to lift a box from the floor to a tabletop. Work done against gravity. Giving the object more gravitational potential energy. We did that last chapter, right? Remember? Okay. Now we're talking about work done against intermolecular forces, separating the molecules from a solid, breaking those crystal bonds that makes us a solid by giving the molecule more potential energy. Again, it's a potential energy, it's a chemical potential energy as opposed to gravitational potential energy. So the two formulas here would be, let me just write them down. They do list them both. I didn't notice that before. If you're changing the ice to water or water to ice, Q is equal to MLF, latent heat of fusion or freezing or melting. All those are the same. If you're changing water to steam or steam to water, then it's MLV. And that's a lot of heat given off when you're changing a little bit of mass from one phase to the other. Now, before we move on from here, there is on page 103 a pretty good size closer look at passive solar design. Okay? The most basic thing you could do, and I think I talked about this before in the heat chapter, you could have, I mentioned my father's first cousin married an architect, and he, way back then, this is in the 40s, the 50s and 60s, he was designing houses, and he had big eaves on them, and put them very close to the latitude, the angle of the latitude, so that in the summertime the sun was above the eave and the glass would not let sunlight through. In the wintertime, when the sun was below that level, then the sunlight came through and gave you passive solar heating. Okay, so you can just use glass that way. I think I also told you, drive sort of my wife crazy by opening blinds and closing blinds, keeping them closed in the nighttime so you don't lose either heat or cooling to the outside. And in the then in the summer, turning the blinds so that the sunlight doesn't come in, and in the wintertime, turning it so the sunlight does come in, just to try to help passive solar heating or lack of heating. You can have other things. One is called a Trombe wall. That is a material that really absorbs the heat better than air does, and you block your window with that, which is not good. My wife wouldn't like that, so we don't have any of those. But then that Trombe wall will then re-radiate, so you have it there in the daylight absorbing the heat, and then when the sun goes down, it's releasing the heat over time into the room. And another thing you could do is an isolated, sort of like a sunroom, having a lot of window space there where it absorbs the heat in the summertime, in the daylight, and then releases the heat in the evening. So it's a whole page worth of passive solar design, well worth a read, by the way. All right. Then there's this figure, and the one on figure 418 and 420 are very, very similar, okay? I'm surprised they have them both in here, but I'll let you take a look. It's the slide we had here. Nope. Well, where was it? Here, that slide. Okay. All right. And your table 4.4 on page 104, left-hand column, that has all three of your specific heats, both of your latent heats of fusion, and it has one other constant you might think of there, and that's the mechanical equivalent of heat, which we've had before in different forms. But let me write that down for you now, too. Here's the way I remember it best. 1 calorie is equal to 4.184 joules. This is, calorie is a heat unit of energy. Joule is the work unit of energy. That's why they call it mechanical equivalent of heat, okay, or mechanical energy equivalent. Now, the way they list it in the book is 1 kilocalorie is 4,184 joules. But to me, those are kind of crazy units to do. Why don't you say 1 kilocalorie is equal to 4.184 kilojoules. Don't mess around with two different numbers. Keep the same numbers if you're dealing with calories, joules, kilocalories, kilojoules. They're the same ballpark, the same order of magnitude. That's the last entry they have there. Now we're ready for example 4.7. All right, this looks like a good place for it. So let's see if we can do it. How much energy does a refrigerator remove from 100 grams of water? So what's 100 grams of water? What's that a measure of? Say again? 100 grams of water. What's that a measure of? No, not weight. Mass. That's the mass of the water. Now, they say this water is at 20 degrees Celsius. What does 20 degrees Celsius bring to mind? That's about what? 20 degrees Celsius. Basically room temperature. 68 degrees Fahrenheit. Nice comfortable. 28 degrees Celsius. What is that a measure of? Temperature. And we'll call that initial temperature because that's what you're starting at. Okay? You're putting in water at room temperature, 100 grams of water, room temperature, you're putting it in the freezer, not in the refrigerator, but in the freezer, at 20 degrees Celsius to make ice at minus 10 degrees Celsius. So you're trying to get this to ice at minus 10 degrees Celsius. How much heat is involved in that process? What processes are going on here? You actually have three. Does anyone recognize them? What's the first thing you've got to do? Say again?
Energy.
I can't hear.
Energy.
Okay, it's all dealing with energy. Okay, what three changes of energy do you have here? You have water at 20 degrees Celsius, you're going to ice at minus 10 degrees Celsius. What?
You have to hit 32 degrees Fahrenheit first.
Okay, which in Celsius is how much?
0.
0 Celsius. So the first thing, you're absolutely right, you've got to cool the water, which means removing heat. What formula would we use to cool water? You're all dealing with heat. So first is the heat of cooling the water. Okay? What formula would that be? It's not one on this page. It was on the previous slide. What was that? What's the formula? You just gave it to me not more than 10, 15 minutes ago.
MC.
Say again?
MC.
MC delta T. Because we have a change of temperature. Well, what's the M stand for? What does M stand for? Mass. And what is your mass? 100 grams. 100.0 grams. Okay? What's C for water? Is what? What was C for water? No, that's your temperature. What's C? Specific heat of water. I wrote it down for you on the other slide.
1 calorie.
1.00 calorie per gram degrees Celsius. And you see the grams are going to cancel out. And what's the other thing you'll need here? Delta T. Well, I see the initial temperature is 20 degrees. What's going to be your final temperature while you're cooling that water? What you going to cool it down to? 0 degrees. So what was your change of temperature? You were at 20, you went to 0. What's the change?
20 degrees.
20 degrees. 20 degrees Celsius. And now your degrees Celsius go out. So this will give you your amount of heat that required to cool that. I didn't leave enough room. Okay, so 100 times 20 would be 2 what?
2,000.
2,000 what unit? What's the only unit left standing? Calories. So if you didn't want to use that big a number, want to go to a bigger unit, smaller number, what would you use? What's the prefix for 1,000?
Kilocalories.
Kilos. That would be 2 kilocalories. 2.00 kilocalories. You don't have to do that, but it's just easier to write than 2,000. Okay, so you've chilled the water down to the freezing point. So what's the next step you've got to do to make ice? You've chilled the water down to the freezing point. What's the next step to make ice? Now you don't stop and think about it, you just do it. But what would be the next step? Thermodynamics. Say again?
Get it to the freezing point.
You got it to the freezing point. You went from 20 to 0. Now you're at the freezing point, so what are you going to do?
You leave it in the freezing point.
You what?
Leave it in the freezing point.
Why you leave it there?
I don't know. Never mind.
No, I think you're pretty close to being on.
Just select the time. You just need the time for it to happen. You just need
Okay. Now, what you remove energy. What happens when you remove energy when it's at 0 degrees?
Freezes?
It freezes, exactly. And what formula do you use for that? It's on the board.
LF.
The latent heat of fusion, right there. And there's the formula, Q. So the next step is you do your latent heat of fusion when you're freezing the water, because that could stand for freezing too. What was the mass? Still 100 grams, okay? And what's your LF?
80 calories.
80 calories per gram. 80.0 calories per gram. And notice the grams go out. And what is 80 times 100?
800.
No. 8 times 100 would be 800. 8,000. What units left? Calories. That's a good unit for heat. That is a unit for heat. If you wanted to do a smaller number, a bigger unit, that would be 8.00 kilocalories. Okay? So you had 2 kilocalories or 2,000 calories to cool the water from 20 degrees room temperature to freezing point. Then you got to freeze the water and make it ice. That was your latent heat of fusion. Don't change temperature at all. You're still at 0 degrees. But you're taking out a whole bunch of heat to freeze that water. But you're not going to stop there, are you? That gives you ice at what temperature? At the freezing point, which is 0. But you want ice at -10. So what have you got to do there? What formula would you use? You use the same one you did before. Okay. Q for cooling the ice is what you're doing now. This is Q for freezing the ice. This is Q for cooling the ice. And what do you use for cooling? Changing temperature. Say again? Same formula. MC delta T. Because you're cooling it, you're changing its temperature. So you've got to have this formula. What's your mass? Still 100 grams. Okay, now it's ice, but that doesn't matter. And what's the C? A little louder? You may have said it, I couldn't hear. What's the C for ice? What did he say?
I didn't say the answer. I heard it.
It was on the last slide.
You know it sometimes. Come on, don't. You just said it.
No, I didn't.
Do you see it?
Yeah, he said it.
What?
I really didn't hear it.
What is it?
He knows it. Tell him,
I
son.
don't know.
It's on the board.
I don't know the question.
Well, then it is hard to get the answer, isn't it?
That's why you keep thinking I keep saying I don't know.
Okay.
Phone a friend.
Alright. Meth guy, what is it?
Second.
What was the question?
All right. We're down here. The heat required to cool the ice. That's why I said QCI, cooling the ice. The formula I thought you said was MC delta T.
That's what he said.
The mass is M. The question was, what is your C?
What is it,
Calories.
No, C is not latent heat, but
Specific heat.
specific heat. And what's the specific heat for ice? It was a long time ago we talked about it, at least 15 minutes.
0.5.
0.50. There, I had it on the thing right here. C for I is 0.500. So 0.500. What units? What units?
Calories.
Calories per
Gram.
gram
Degrees Celsius.
degree Celsius. Now, what's your change of temperature of the ice? Second? Okay, you're going to minus 10. From where? From 0. So what's your change of temperature? Okay, 10 degrees. We won't mess with the minus sign. You're changing it 10 degrees. So 10 degrees, 10.0 degrees Celsius. And degrees Celsius go out here, if I could find it. And grams go out here. And you've got 10 times 0.5 times 100. What would that be? 500. 500. What units left? Calories. So if we use calories, it would be 2,000 for the cooling of the water, 8,000 for changing it to ice, and another 500 to cool the ice. So that would be 10,500 calories. Or if you use smaller number, bigger units, 10.5 kilocalories. Okay? Does that make sense? Or you could say 10,500 calories is what would be required, or 10.5 kilocalories. Okay. Boy, I felt like a dentist there. Pulling teeth. Okay. All right. Any questions on that? That was 4.7. Guess what, team? We're going to be doing something very similar to this in lab today. That's why I wanted to go over this.
Yay!
Yay! All right. Good stuff, Maynard. Okay. Yes. Can't control yourself, can you? Okay. All right. We've already looked at that slide once before. So here is sort of a table showing these phase changes and giving some of the nomenclature. When you're going from a solid to a liquid, that's obviously a phase change. It's not a change of temperature, it's a phase change. It's called fusion, solid to liquid. Actually, we call it melting, but if you went liquid to solid, it would be freezing. You call both of those the latent heat of fusion. Okay? When you're going from a liquid to a gas, we call it the latent heat of vaporization. For water, what was the latent heat of fusion? It's been a while. No, that was specific heat of water. Liquid water. Latent heat of fusion. Boy, retention's really good, isn't it?
80 calories.
Yeah, I went past it right there. 80 calories per gram, right there, latent heat of fusion. Okay? Latent heat of vaporization?
540.
540 calories per gram. Now, you can go, and it doesn't happen too frequently, you can go directly from a solid to a gas. That process is called sublimation. Okay? Water does it, but at a really weird temperature and pressure, so we never really go there with it. But there are materials that do it at normal temperatures and pressures. Does anyone know of one that sublimes, going straight from a solid to a gas?
Dry ice and water.
Dry ice goes to water water vapor. Doesn't go through the liquid phase. Where do you see that sometimes? Rock concerts, when they have the vapor and stuff there, that's dry ice there. That's going straight. You're not seeing water vapor. You're seeing the cold water vapor then hitting the warm air and condensing into basically a cloud, with the water droplets. That's sublimation. Runs directly from a solid to a gas. Now the temperature, if you're going from the solid to a liquid, we call that the melting point. And it's the same temperature as going from a liquid to a solid. Then we call it the freezing point. Same temperature. For water, 0 degrees Celsius, 32 degrees Fahrenheit. Same temperature, it's just which way are you heading? Are you melting the ice or are you freezing the water? Okay. When you're going from a liquid to a gas, in that direction, adding energy, you call that the boiling point of water. However, if you're going this way, it's the condensation point. Okay? That you're condensing the gas to a liquid. Where does that go on? Where do you see evidence of that happening? In the air. When you have a rain shower, it's going from water vapor becoming droplets of water that fall to earth. That is condensation. Another thing, I think any of you, possibly. Okay, if you had put a whole bunch of ice, or if you had a whole bunch of ice in, say, your water or your juice or whatever you got there, now probably not that one so much, but if you had it, especially in a aluminum can, very cold water, what do you notice happening on the outside? Glass, it happens all the time. Water droplets, okay? We were working, when I was working at Southern Research Institute, with a guy, really good scientist up from upstate New York, Schenectady or somewhere up there, who was really one of the experts in air quality and stuff, and we were working with him, and there was a meeting going on down in Orlando, Florida. And he was amazed that you could pour ice water into a glass and immediately you had condensation on the outside of the glass. He said he did not know it could happen because upstate New York, the humidity is not that great, and you usually aren't that awfully hot up there either. So you seldom say he had never seen that. He said, look how fast that's happening. He just could not believe it was almost instantaneous. You put the cold water in the glass, immediately you get water on the outside. That's condensation. Now when you go from solid to a gas or a gas to a solid, you call both of those sublimation. Seems crazy to call it the second one, but you call it that anyway. We don't have the constants for that because we don't really do that very much. You can look them up and find it for different materials. Okay. Now, let's consider those concepts of evaporation and condensation. Evaporation is when the sun hits the surface of the ocean, say, the Gulf of Mexico, and evaporates the water out of it. That's evaporation. Condensation is when that water vapor goes over, say, a mountain range or something like that, cools off quickly, falls out of the air as either rain or snow. Those are examples of evaporation and condensation. What's going on there? The individual molecules can change phase at any time. It's whenever they decrease in energy or increase in energy enough to change the phase. They don't have to be at a certain temperature because that individual molecule's average kinetic energy could be at the vaporization point, where the air temperature isn't, but that individual molecule may be. Okay, so that's why it can change phase at any time. So evaporation is the energy required to overcome the phase cohesion, the water molecules sticking together like they do and escaping and become water vapor. The higher energy molecules near the surface can then escape. Now here's the visual of that. And this is just representative. They're not giving any units here, but let's just say the water molecules down here are at 5, whatever your units are for kinetic energy. Some are at 10, some are at 15, and some are at 25. And say at 25, they got enough energy to become water vapor. Okay, so these are relative units here. So what's the average kinetic energy? Well, here we have 50, 60, 70, 80, 100, 115. So 115 divided by 4, 5, 6, 7, 8, 9, 10. 10 molecules, or representative molecules. That's an average kinetic energy of 11.5. So that's going to give you some temperature, okay? Let's just say that's about room temperature, okay? Just to have something. Average kinetic energy about 11.5. Some of these molecules quite a bit colder, some of them quite a bit warmer, okay? More energy in them, okay? Now, is this realistic that the lower energy molecules will be near the bottom, the higher energy molecules at the top? Higher kinetic energy going to bounce each other away from each other, so they tend to be less dense, and the cooler ones are more dense at the bottom, right? So yeah, that sort of makes sense. I would expect more of the 5s to be down here and the 10s and 15s to be in the middle, but that's generally what you got. But your warmer, higher energy molecules are going to be near the surface. Well, if 25 is enough kinetic energy to escape, let's say we lose those two, okay? The higher energy molecules near the surface can escape, okay? So what happens then? You have lost 2 molecules, so you go from 10 to 8 molecules, representative molecules. But whatever you got left 10, 20, 30, 45, 50, 55, 60, 65. 65 total kinetic energy divided by 8 molecules, you're down to 8.1 average kinetic energy. A good bit cooler. Okay? Right? Now, I've never had one of these, but I've seen pictures of people who did, and they do it out west a lot. They carry water, like when you're hiking and stuff like this, in a canvas bag. So a little bit of water can go to the surface and evaporate. But the water inside then tastes really cool. It doesn't get that hot, and the reason for that is that you're evaporating the high energy, dropping the average kinetic energy, and the water stays fairly cool. Whereas if you just have it in a bottle, it's going to soon be at the same temperature as the air around it. You drink it, and it's like drinking tap water, okay? So it's not that great. So that's what's happening. Condensation or evaporation tends to cool a system. Where do we use that? Y'all use it. When you're
The condenser in the AC?
in your AC unit. Exactly. That's exactly what's happening. What you do is heat it first, right? and make it into a vapor, blow that heat away, and then you let it condense again. And when it condenses again, you have a cooler environment. And that's the air that you pump through the interior of your car if you've got the air conditioning on. Or if you're refrigerating something, or if you're freezing something. The whole process is like that. So condensation, the gas molecules near the surface lose kinetic energy to the liquid molecules and then merge back in. So if you had a cool situation, a very cold situation, you can actually have frost building up on the outside of your, and that happens in your air conditioning line sometimes, doesn't it? When you have the condensation, not just condensing, but then also freezing. So you can go through the whole spectrum of activity there. All right, now we're in, we're in 2.5. This is on page 106. And by the way, here's a figure here they don't show in the slide set. In the old days, I can remember my mom had a solar energy clothes dryer. It was called the line. And you hung up the clothes on it, and the clothes dried out there. You know, they actually smell pretty good, you know, if you're out in fresh air. We lived out in the country. Sometimes would be a little stiff maybe, but, you know, if you had much wind, they stayed pretty cool too. So why we're not doing that, I don't know, but no one wants to hang out clothes much anymore. Okay? There is also a little blurb here, concepts applied. Why is it called the pop can? Frankly, I found that a little bit of a lame one, but what happens when you do open a soda can? It does pop, and why is that?
It's release pressure.
Okay, why is that the case? Because
it's fresh when you have pressure on it.
yeah, they pack it with the gases at a pressure which keeps the gas dissolved in the liquid, and when you release that pressure, then the gases tend to come out, and that's why they fizz once you open. And that same thing, opening a bottle, you'll see the fizz start happening because you release the pressure. Okay, let's move on to thermodynamics. I think we talked about where this word comes from before, right? Prefix thermo has to do with heat, temperature. Dynamics, changing situations. The changing of heat, the transfers of heat. Thermostatics would be everything at the same temperature, at the same thing. So this is thermodynamics. Things are changing. It's the study of heat and its relationship to mechanical and other forms of energy. Basically, in a nutshell, that's what thermodynamics is. Thermodynamic analysis includes you look at the entire system, not just the individual components, but the entire system. That may include the surroundings, and we'll deal with that a little bit in the lab today too. The system is what you're studying, the surroundings are everything outside the system. You'll be looking at internal energy, that's in total internal and kinetic energy of the object in question, but basically thermodynamics is looking more at the macroscopic scale. It's influenced by the internal, but you're considering mostly what's going on the outside. But you have to take that into account. So, some of the energy conversions we have, okay? And I think Yosei or someone mentioned friction earlier. That converts mechanical energy to heat, okay? Rubbing your hands together, you can feel them get warm. The friction of your palms on each other, that is creating heat, okay? In your automobiles, of course, that's the friction between the parts. Now, hopefully you minimize that by what?
Oil.
Yeah, your lubrication, whether it's oil or grease. You minimize that, but there always is some. Now, most of your heat that you're dealing with is coming from the combustion process, but there is some coming from the friction. Hopefully you minimize that. But you know, your tires on the road, ever felt of a tire when you first come in after a long drive? Quite hot, okay? And then, of course, if you've done any braking, as long as it's not regenerative braking, if you've done any braking, those brake pads and drums are extraordinarily hot. That comes from friction, converting mechanical energy into heat. Now, heat engines, that's your engine on your car. That's your internal combustion engine. Devices that convert heat into mechanical energy. You're burning the fuel, pushing the piston down, making it move, turning the drive shaft. That's your heat engine. Devices that convert the heat into mechanical energy. Other applications, heat pumps are basically reverse of refrigeration or air conditioning. What you're doing is compressing a gas, producing heat, and then pumping that heat off of the hot gas into your house or wherever you're wanting to heat. Whereas on the other hand, if you're cooling, refrigeration, that type of thing, you blow that heat away to the environment and then in your condenser let it expand again, and that gives you refrigeration. Now, organisms are other things that convert heat, okay? If you get sick, fairly sick, what do you sometimes have?
Fever.
A fever. That's because the germs, the microorganisms, your body is trying to fight them, and you're producing heat. So organisms do. You exercise, okay, you produce more heat, okay? Now, of course, on the global scale, when the equatorial regions of our planet get too hot, they produce hurricanes and send them north or south, to send the heat to the other parts of the planet. I was actually in a book study at one time, didn't go there, but one time, and it was at church, so it was talking about one thing, but someone said, and I happened to be in the study with Jerry Tracy, okay, and someone said, I don't know why we have hurricanes and other natural disasters like that. Why do they even allow it to exist? And Jerry said, well, you got to have them. If we didn't, the planet couldn't survive. Because the heat would build up around the equatorial region. If you didn't have a way to dissipate that, you get too hot down there, too cold at the poles, you can't support life. So that is a natural process of heat distribution in hurricanes. Stars, you have fusion, nuclear fusion going on that is producing the heat and the other things. Black holes, who knows what's going on in there? Whatever it is absorbing everything, even light. That's why it's a black hole. Light cannot escape a black hole, so everything is getting sucked into that. Virtually any system with energy inputs and outputs, they're somewhere here in energy conversion. Thermodynamic systems, okay? And you consider the whole system. All right?
Can we take a break?
Yes, we can, okay? Guess this is a bad time. So we'll start, and we'll come back with the first law of thermodynamics.
Oh, I meant to turn on the projector first.
Yes. I'm sorry.
Can I get that live from Tuesday?
I thought you picked it up before you left, but you didn't. Okay. That's it right there. Okay. Okay. What's that?
That's what the live on Tuesday.
Were you? Oh yeah, you had to leave. She didn't. Oh yeah. That's too far. Not far enough.
It's going to be a short nap you do today.
Well, it's going to take a while to set up, but once it's set up, it won't take too long. Okay. All right, we've been recording now for a few minutes of me passing out papers. All right, let's look at, we're not going to look at all three, but I'll mention all three. In fact, some people claim there's 4 laws of thermodynamics. I think I mentioned this before. some people refer to the 0th law of thermodynamics, which basically is your why you can have thermometry that works, okay? And it's basically that when two objects are in thermal equilibrium with each other, let's see, how do you say that? If object A is in thermal equilibrium with object B is in thermal equilibrium with object C, object A and object C are in thermal equilibrium. It's basically that. Meaning that, say with a thermometer, which we use in lab Tuesday and we'll use the lab again today. You have the material you're trying to measure, you have the liquid inside the thermometer that is doing the measurement, and they're in thermal equilibrium because they're each in thermal equilibrium with the glass tube that contains the liquid, okay? So that's always sometimes called the 0th law of thermodynamics. Now, the first law, and the reason they didn't make it the 4th law, the other three depend on it, but everybody just assumed them to begin with. The first law, this is the one, by the way, William Thompson was largely responsible for organizing and stating these. Many other people contributed, and his name or his title, anyone remember what that was? Lord Kelvin. The one that the Kelvin absolute temperature scale is named for. Basically, the first law of thermodynamics is just a restatement of the conservation of energy. Okay? The components here are internal energy, which we've been talking about, the total internal energy that can be potential and kinetic of an object. You've got heat, which is energy you're either adding or losing from the system, and then work that you're either doing to or is being done on the system or by the system. Okay? So those are the three components that you have going on. Internal energy, which can either be increasing or decreasing. Heat, which is being added to the system or given off by the system. Work, which can either be done to the system or being done by the system. Now, it's stated in terms of changes of internal energy. That's what we refer to it. So quite often, the symbol here is delta IE. I think this book uses delta U. Same thing, okay? Example or applications of this are heat engines, okay? And we'll look at that in just a minute. Why don't they give the formula? They don't, okay? So let me give it for you. Let's see if they are going to give it in a minute. Nope. Okay. Let me give you the equation that represents the first law of thermodynamics. And they use a sort of a strange nomenclature for it. They use JQ, okay? Now JQ, J is the joule equivalent of heat. Remember the 4.1 of 84 joules per calorie, times Q, which is calories, so that gives you joules, minus W, that's the work, and this is equal to the change of internal energy, U1 minus U2. Okay? So this is the heat proportion, this is the work part, and this is the change of internal energy. Okay? So that's how we express the first law of thermodynamics. The change of internal energy comes from heat added minus work done by the system. Okay? So let's take a look.
That's JQ minus W.
JQ minus W is equal to U. I put the things backwards. It's U2 minus U1. Sorry. Yeah, sorry about that. It really does. It depends on how you define it, but the book gives it as U2 minus U1. That's change of internal energy. The difference is delta. So delta U is what I usually call it, or delta IE. Okay. So here's the example of that. Whoa. Okay, should have put it there. Okay. So here is what we have going on here. let's just say that we have a cylinder of air molecules, okay? And let's say that at the beginning, the piston is up here near the top. And you put a weight on it. What is that weight going to do? It's going to compress the air molecules beneath that. And when you compress them, you make them closer together, they're going to run into each other, they're going to heat up. So the amount of work done by the weight compressing those is related to the amount of internal energy you've increased in the air molecules because of heat, okay, friction. Now, what if you take a flame and put it under that cylinder, okay? Well, now you're going to, the air molecules are going to get hot, they're going to expand, they're going to lift the weight. So now they're doing work on the system. Right here, the weight was doing work on the system. Now the system is doing work on the weight. It's lifting it, increasing its gravitational potential energy. So the first time when you put it on, the environment was doing work on the system. Now the system is doing work on the environment. And that, yeah.
Does that kind of translate to like an explosion? Of like
Absolutely.
A gasifier?
Exactly. If you could picture this as your spark plug in here or whatever, you know, and there you're igniting the fuel, then you're doing work on the system. It's not a weight that you're doing, it's pushing the whole drivetrain, basically, ultimately. Okay? That's exactly what this is equivalent to. And that is a heat engine. The heat is doing work on the system. Okay. And that happens in internal combustion engines. Now here's another way to look at that sort of in a diagram. What you have is a low temperature region, that's your QL, that's here, okay? Well, no, that's actually, Q is over here. Low temperature region, you have a high temperature region, so you've heated the thing up. As the heat engine does work sends work to the outside, that's why it's minus W, okay? There's some low energy, some low temperature region left over. This is the heat engine, you're doing work with the heat engine. Here's the sad news. There's always a low temperature region. You can't get very much more work out of that. You still heated it above the atmospheric environment, but you've gotten all the work out you can. There's always energy wastage. That's why your efficiency is pretty low, okay? And unfortunately, heat engines are not the most efficient, okay? All right. So that's the first law. The second law of thermodynamics, the zeroth law being basically equilibrium of thermal equilibrium, how that happens. Okay, the second law of thermodynamics, you can state it three different ways. These are equivalent statements. And they don't sound like it or seem like it to begin with, but they are. No process can solely convert a quantity of heat to work. We just saw that. There's always some wasted heat down here, low energy heat, you can't really use to change to work. And that's what heat engines do, okay? No process can solely convert a quantity of heat to work. You always have some wastage, okay? So that's one statement for the second law of thermodynamics. The other, and this seems a little bizarre, heat never flows spontaneously from cold to hot, okay? It just doesn't happen. Refrigeration does not, heat never spontaneously goes from cold to hot. It's always in the other direction, okay? This is sort of a kind of a dumb explanation of that. Let's say that your AC went out in your house, okay? Your house was sweltering hot, okay? What about the idea the AC went out, but the electricity didn't go off? So why don't you open your refrigerator and freezer doors and let that cool air out and cool your house that way?
It's not going to be able to cool it.
What's that?
It's not going to be able to cool it
Why not?
because the cooler inside the fridge is only meant to cool that small area, not house.
Okay? I contend it'll actually make it warmer. It'll actually make it warmer. Why?
Because it's overworking itself.
Okay? What's this? If you picture your refrigerator, okay, most refrigerators, the condenser is inside the kitchen too, isn't it? Your, that is too, but your compressor, did I say compressor or condenser? Okay. The compressor is there somewhere in the back of the fridge, okay? Your compressor, okay? You're blowing heat off, that's why the vents and plates and tubes and stuff are in the back there, and you're blowing heat out, and then you're pumping the cool inside. Open those doors, yeah, you get cool coming out, but all the heat that's making that cool is coming from the back of the fridge. It actually increases the temperature of the room, not decreases. Okay, maybe right in front of the fridge it will feel cooler, the whole room will get warmer. Heat never flows spontaneously from a cold object to a hot object, as in the refrigerators. And here's the third. Natural processes tend toward a greater state of disorder, and that state of disorder is called entropy. Natural systems, natural processes always tend toward a greater state of disorder, never of order. Now here's a really dumb example of that. Let's take a brand new pack of playing cards. You've seen one before, right? And usually when you open that pack of playing cards and look at them, usually they're ace through the deuce of spades, and the ace through the deuce of hearts, and the ace through the deuce of diamonds, and the ace through the deuce of clubs, right? They're in that order usually when you open a brand new pack. They're like that, right? And they're all facing the same direction too. So let's open that pack, put the cards on a sheet, 4 people stand at the corners of the sheet, and throw them up in the air. And catch them all in the sheet, okay? And do that till the cows come home, okay? Are you ever going to get them to line up just the way they were together? They always go to disorder. They never revert back to the same order they were before. In fact, you will never get them all lined face up or face down, okay? They're always going to be randomly disordered. That is the second law of thermodynamics. Natural processes tend toward a greater state of disorder, as in your room when you were a kid, and maybe right now. Doesn't everything tend to get out of order?
Yes.
Unless you put the energy in, or Mama puts the energy in to put it back in order again, everything tends to disorder. Okay? Those all three are stating the second law of thermodynamics. No process can solely convert a quantity of heat to work. You always have some wastage. It never flows from spontaneous from cold to hot, and natural processes always go to a state of disorder. Here are some reference scales for that. The object's external energy, that's the energy of the global coherent motion. Like if I pick up this thing and throw it to Chris, okay, I'm giving it kinetic energy. That's the external energy, okay? That's associated with work. I do work on it to make it have that energy. But you also have the object's internal energy. The energy of the microscopic, chaotic, incoherent motion that's involved with that, that's associated with heat. That would be like if I took this and rubbed it a lot. I will make that get warmer, okay? Okay, not a good thing to rub, but it will make it associated with heat. This is probably a sort of a dumb example of that too. Have you, I'm sure you have, had a wire and you're wanting to break the wire, cut the wire, but you don't have any snips or anything to do it. Take the wire and just do this.
Yes.
Then after a while, and it gets hot, okay? But it also will ultimately break because you're increasing that microscopic, chaotic, incoherent motion that's associated with heat. Your action, your work you're doing on it is doing that. So that is some work, but it's also contributing to that as well. The other example here that I think the book is going to give in a minute, well, I'll just let them give it. Okay. All right, so that first statement, conservation of energy, the heat engine, okay? Now, the input energy supposedly equal to the output energy. It is, by the way. It always is. Input energy equals output energy, okay? Conservation of energy. However, not all of the output energy is useful energy. Some of it goes to that low temperature source, some of it goes to work. You'd like it all to go to work, some of it's always wasted, okay? So the efficiency of the heat engine, the work done per unit input energy. So you see your input energy is what you put into it. The output energy is the total out. Some of that's work, some of it's waste. The output energy, the second law basically says energy, the efficiency cannot equal 1. Ever can the output, the efficiency equal 1. You'll never get all the work out that you put in, okay? Some energy is always degraded, and usually it goes to low-level heat that we can't use. Now, just yesterday I was talking with Dr. Bryant, who teaches physics here, and I teach some physics here too, but usually fall and spring he teaches it. Have y'all heard of nanotechnology?
Yes.
Okay. Basically, they call them nanobots, little things that convert very little amount. I've heard this described, I don't know exactly how, but they can sometimes embed these things in clothing. And as you exercise or move or just walk, and there's a lot of wasted motion, heat is given off, they capture some of that and convert it to electrical energy. And you can use that to recharge your phone or your devices or other things, because you're actually converting some of this wasted, degraded energy into electrical energy. Okay, never can they catch it all and do it all, but that would be a very nice source if they can perfect that technology of keeping from having as much wasted energy. Okay? Here is your basic formula for this. Oh yeah, I meant to say this. In your text, let me go back to the first law again. Okay, remember, I gave you this one, that the heat, that's JQ, it takes Q in calories and using the joule equivalent of heat gets it into energy unit, joules say. Joules of heat minus the work gives you your change of internal energy. Now, if by chance you have a equilibrium situation, in other words, that your change of internal energy is 0, okay? Then, if you use this, if this right here is 0, change of internal energy is 0, then JQ is equal to W, okay? Well, what is your JQ? That's your joule equivalent of heat. This is your Q high minus your Q low. And this refers to that diagram we had before. That would be the work, okay? If that was 100% efficient, this would be the case. It never is, okay? You never can get all this change of energy here, change of heat, to convert to work. It never happens. But if you can get close to it, that's the second. And that's equation 4.8. I meant to point that out to you when we were on that. Okay. So, back here. This is now QH, and this is what reminded me, because that formula had QH in it too. If that was indeed true, your high energy heat, high heat field, is going to be work plus QL. Remember our picture? QH was up here, some went to work, some went here. So this is just saying that QH is equal to the work produced plus the heat that's lost. And there's always heat that's lost. Always, okay? The efficiency of your engine is the useful output divided by the total input. And since QL is never 0, this ratio is never equal to 1. This is called efficiency. Since there always is some heat loss here, the work done is never equal to the total input. Ever. Okay? I think I've mentioned to you before, and this is just a ballpark figure I remember reading years ago, so it may be gotten better. Your efficiency for an typical internal combustion engine, I'm not sure ever exceeds 20%. I don't know. Do y'all deal with those? That the efficiency of a internal combustion engine, I don't think will ever get much better than 20%. Maybe today they've gotten close to that, or maybe a little better. Back when I remember, it was like 15 to 17% was the best. Because think about how much heat is blowing out your tailpipe. How much heat is blowing out of your radiator. That's all QL. That is heat that you're not using. You can't possibly use. Yeah, you're getting work, you're doing this, but a lot of this heat is bypassing the whole system and is lost going to the environment. Okay? So, here is the second statement of the second law of thermodynamics. Again, conservation of energy. This time we're looking at a heat pump. Okay? With a heat pump, what we're doing is the work is going into the system to compress the gas, say, and that's creating a high temperature region here in the compressor, right? You're pulling that gas from a low temperature region, okay? The heat pump is then taking it's doing the work to create the high temperature, and then you blow this off into the house or wherever you're trying to heat. The work is required to move the energy from the cold region to the hot region. It never goes in this way by itself. You have to do work on the system to increase the energy. You have to. And that's just like your room. The only way to keep it from going to total randomness and disorder is to clean it up, straighten it up, put things back in order. It doesn't happen spontaneously. You have to add work to the system. So that's what we say. To get from here to here, you have to add work. It never goes this way independently. Okay? The energy arriving in the high temperature region is energy from the low temperature region plus the work needed to move it. And the upgrading of energy by the heat pump is accompanied by greater degradation in energy elsewhere. Wherever was producing this work, that's what it's kind of like, this isn't quite the same thing. All that's going on in the compressor and the coils behind the refrigerator, that's more work than you're getting cold coming out. That's why the temperature in the room actually goes up if you leave the refrigerator door open. And here's the third stage. Real processes are irreversible processes. They never, ever tend toward order. The measure of this order is called the entropy. And the second law in those terms, the total entropy of the system or the universe continually increasing. The randomness is increasing. Okay? Now, the ramification of that is one of these days the whole universe will die heat death because everything's going toward randomness. Okay? Natural process, and that gets back to what in the world was the Big Bang anyway then, because that's what got things moving. Something had to, too big for this class, for me to think about it. Natural processes degrade coherent, useful energy. Everything tends to incoherent, chaotic, non-useful energy. Available energy of the universe is diminishing, eventually heat death of the universe. Okay, that's sort of scary, but I guess it's true. Not during our lifetime, though, okay? Our sun's good for another 5 billion years. I don't think we'll be around to see that, okay? The direction of natural processes always toward more disorder, and their example is spilled milk will never unspill itself back into the glass. Ever. Don't wait for it to happen. Okay? It's not going to happen. Okay, just by the hair of her chinny chin chin, she's in for the first part. Chelsea's here. All right. There's the second law of thermodynamics. Now, myths, mistakes, and misunderstandings. Well, let's see. What's the next one? Oh, that is the last one. Bottom of page 108, myths, mistakes, and misunderstanding. It makes its own fuel, okay? No, it doesn't, okay? Nothing is going to, if you hear something like this, in fact, I believe it was attempted here using some of the what you might call unused energy in an internal combustion engine to turn a generator to generate electricity to electrolyze water into hydrogen and oxygen, and then taking that hydrogen and oxygen and burning it to do, you know, it's a good idea, okay, but you're making your own fuel. No, you're not. You're taking just as much energy to electrolyze the water as you're going to get out of it burning it again. In fact, everything tends to randomness. You're actually going to lose in the process, okay? So that's part of what this is talking about. I'll let you read this to see it again. Other people talk about perpetual motion machine. Do not exist, okay? Cannot exist, not in our universe. Now, there's a fairly interesting blurb on the top of page 109. People behind the science, a guy whose name was Count Rumford. His actual name was Benjamin Thompson, with a P, not like William Thompson without a P. That was Thompson. This is Thompson. He was actually American. Well, kind of. Back when we were the American colonies, so he was really British. But he was a very good engineer, brilliant engineer. The sad news is he didn't agree with our move toward independence. So he resisted that. He may have even, there are some implications that he may have been maybe somehow connected with Benedict Arnold and some of the others who were either spying on the revolutionaries and, you know, helping England. Anyway, he fled to England, and because he did flee and he was a very brilliant man, they rewarded him by making him a count. He hadn't been a count before. He was just made a count to reward him for sticking with the home team, you know. And as such, he used his engineering skills for a variety of things, and he was at one point working for the Germans. Germany was, you know, manufacturing some munitions. I think they were making cannons. And basically what they did back then was used cast iron and made the mold for the cannon. But then they had to drill the hole to put the cannonball and the fuel and that kind of stuff in. So they cast the whole thing and then drilled out the middle. And he was in charge of doing that, and he was a pretty good scientist and engineer, so he was always thinking. That was a pretty mundane thing. Back then they had horses that were turning a big treadmill, and that was turning the bit, and the bit was drilling the hole. Well, the bits would go dull pretty quickly, so they always had to be changing bits. And he noticed, clever man that he was. Now, before this, you got to get the idea before this. Before this, Aristotle said heat was one of the four basic elements. Earth, wind, air, and fire. Right? Fire was an element. So that meant that the fire was, and he used the example of wood. Wood, you burn wood, it goes into air, it goes into earth materials, that's the ash. The air is that, the heat is given off too. And he said it has to be an element. And that's what everybody believed. Even this late in history, people believed that fire was actually an element. You couldn't really measure it, but it was somehow part of the material. So what Count Rumford did, he was observing, when these bits get old and dull, they don't grind the metal, but they produce a lot of heat. He said, this can't be true if Aristotle's statement was true, and everybody believed it. So what he did, he was doing this, I think, near Munich, and Munich is not too far from the Alps. I mean, it's a fair little distance. So what he did was intentionally took a cannon thing that was faulty, that he couldn't use. It was off-center. I don't know why it was. So anyway, he took the oldest, dullest bit he had, got his poor horse to walking around, and he filled, before he started walking the horse around, filled that cannon shaft, completely full of the coldest water he could get, right off the Alps. Cold, almost freezing water. Filled it with that. Started the horse walking around with the dull bit in there, and within, I think, an hour, he had that water boiling. And he said, look, there's no material producing this. This is the work of the horse is changing to heat energy. Fire is not an element. It's another expression of energy. He was the first to come up with, Joule is given credit for it because Joule actually went through and quantified it. He just did the experiment that showed, look, this is a function of work. It's not a function of the material itself. That was Count Rumford. Interesting character. If you haven't chosen a paper topic yet, he would be a pretty good one, I would think. This cannot be your source. You have to get your source elsewhere. This can give you the idea. You have to get your source elsewhere. Which, while I'm on the subject, let me mention this. Here, my third largest class that I've taught this term, and we're well over halfway through the term. Uno paper has been turned in. Thank you, Melva. Okay? One paper. That's all. Folks, you got 3 weeks after we come back. 2.5 weeks to turn in your paper. Take advantage of your week off. Get your papers done. Otherwise, when you're trying to do finals, when you're trying to wrap up everything, do your last minute projects and things, you're going to be having to write a paper too. Don't put it off. Get it done. I expect to see lots of papers come in Tuesday after Thanksgiving. All right. There is one more example in the end of this chapter. And let's see if we can get some room here. Here's a nice place to write it. A heat engine operates with 65 kilocalories of heat supplied. 65.0 kilocalories of heat supplied. Now that is what we call our QH. Okay? QH. That's how much you're putting into the system. That's the amount of energy, the heat you're putting into the system. Okay? And exhausts, this is what's blowing out the tailpipe or wherever, exhausts 40 calories of heat. 40.0 kilocalories of heat. That's your QL. That's the wasted, the non-usable heat energy. The top is your input. This is part of your output. The question is, how much work did the engine do? Okay? If you go back to this formula right here, QH is equal to W plus QL. If your QH is 65, your QL is here. How do you get what W is? The difference between those two. And what is it? Can you read it through that? Say again? Okay. 60 and 40. 65 and 40. What is your W then? This is your QH, that's your QL, W would have to be. No, you're not adding. This is the high, that's the low. The work plus the load equals the high. So what would that be? 40, 25. So how much work did the engine do? The work done by the engine would be QH minus QL. Subtract QL from both sides, and that would be 65.0 kilocalories. The QH minus 40.0 kilocalories. That's your QL, and that would be 25.0 kilocalories. Except we don't usually measure work in kilocalories. How do we usually measure work? Joules, exactly. Okay? Now, how do we convert kilocalories to joules? Well, it's a conversion, so you multiply two blanks, and you're trying to get a blank number of joules. So, again, like we do all our conversions, always put the units in their place. This blank is for numbers, this blank is for units. Do the units first. What unit goes where? One goes above, one goes below. What goes where? Here are the two units. One goes above, one goes below. Which one goes where? Joules have to be on top, absolutely. And kilocalories on the bottom. So your kilocalories can cancel out, and you got joules where you want them, right? Now we go back to the pretty exciting stuff, huh? Always. Here we have, no, is that it? Yeah. The joule equivalent of heat. You see it up there in the upper left? Okay, 1 kilocalorie is 4.184 kilojoules, right? Okay, so you go back here. You got that in your head? 1 kilocalorie, 4.184 kilojoules. Oops. That was it. Okay. So 1 kilocalorie, 4.184 kilojoules. So this will give us our answer in kilojoules, not joules. So multiply 125 times 4.184. What you get? Yeah, you multiply the numerators, you divide by the denominators, that's 1. So there's no division. Anyone got a calculator? Anyone? 105, yeah. 105 kilojoules. It rounds to 105 kilojoules. All right. Now the question they didn't ask here, and I will ask it, what was the efficiency of this heat engine? What was efficiency? E is equal to? Second?
W over Q.
All right. Whoops. W over, what did you say?
Q.
QH. Okay. So this was work out was 25. Work in was, or heat in was 65. And keep it in the same unit. Don't use your kilojoule unit. Keep it in your kilocalorie units. And someone do that. 25 divided by 65. Second?
0.38.
38. That would be your efficiency. That would be 38% efficient. And that's probably a pretty efficient engine too. Boo hiss. Okay, bad news. All right. They didn't ask that, but that was easy to do at that point. There's a little concepts applied here, law of thermodynamics in action. Worth a read to see. I would be careful if I were doing that, but yeah, you can take a look at that and see. Now, I say this every chapter, and I'll say it again here. Nothing replaces reading the chapter. Okay. Yeah, Melva's been in the class, and Chelsea too. 2 terms in a row now. Nothing replaces reading the chapter. However, once you've got it read, the summary does a fair job of summarizing the high points. Doesn't cover everything, but it does a pretty good job of hitting the high points. It's a pretty good sized summary too, compared to some. Summary of equations, you got 8, which is about normal, maybe a fewer than some chapters, more than others. Key terms, about normal it looks like, but they give them alphabetically, but they do put the page numbers where they're both either first introduced or described or defined. But then the best thing I think for studying for the test are you're applying the concepts. 43 multiple choice questions, way more than you'll have on your test, and they're not going to be the same questions as the ones on the test, but they're going to cover the same material. If you can get those right, and I would say do that yourself, compare the answers. They give the answers here. If you don't get the right answer, figure out what you did wrong. If you can't figure out, they may have made a mistake, or ask me and we'll see if we can figure out why their answer is right and yours may have been wrong. Questions for thought? Maybe a few more normal than normal. 17 on in this chapter, 7 for further analysis. I know that's a few more than normal. There's a little blurb here on invitation to inquiry, who can last longest. That would be maybe interesting, but I don't think it'll be all that helpful necessarily to the test. But then the parallel exercises, 17 in Group A, 15 in Group A, 15 in Group B. Group A has their answers in the back of the book, Appendix E. Group B does not. Those are well worth looking at. You'll probably have a couple or 3 calculations. They'll be more like those Group A questions. So take a look at those. All right. Any questions then on Chapter 4? So Tuesday after we get back, the last 30 minutes will be on that chapter. Let's get out of this and let me at least introduce to you Chapter 6. We're not going to do Chapter 5. It's a great chapter, Wave Motions and Sound. A lot of interesting stuff there, but we just don't have time to do it. So I figured the electricity and magnetism chapter is more pertinent to most of you than wave motions and sound. Both important, but this is probably a little bit more so. So let's go to Chapter 6, and let me at least introduce it to you. I don't know why this is not responding. Here we go. All right, we'll pick up here from the current slide. A pretty neat picture here, electricity. This chapter is on electricity. However, a better description of the chapter would be electricity and magnetism, because we're going to look at both of these. Now, this is an incredible shot of a lightning strike. Now, what you can't tell about this lightning strike is whether it's coming from the cloud going to the ground or whether it's coming from the ground and going to the cloud. I would say it's going this way because you can see these branches are going off that way. So I think this is cloud-to-ground lightning. But I have seen pictures, someone just happened to snap it right at the right time, and you see that it's actually going from, occasionally you have ground-to-cloud lightning as well. And then quite often you have cloud-to-cloud lightning, so you can have all of those. Okay? And why that was on a full moon night, I don't know. no clouds in sight. I don't know. I think someone photoshopped something there. I don't know. Yeah, I believe so. Okay, here's the core concept, also given on that same page. Electricity and magnetism. The electric and magnetic fields interact and can produce forces. They do produce forces. And they don't really exist independently of each other. We think of electricity as one thing, magnetism as another. In reality, they're two halves of the same coin. Okay? Electric and magnetic fields interact and produce forces. Okay? So some basic concepts here of electricity. Okay? This is 6.1. Let's start with the atom. And this is called the electron theory of charge. Now, way back in history, people knew electricity existed. They didn't know beans about why. In fact, most people today don't know why it exists. But the old thing that people used it for was a parlor game. If you had a group of people together, well, let's get a piece of amber and rub it with fur and then touch somebody with it and shock them. Oh, ha, 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 fun, you know. Make them, you know, yell, scream, whatever. That's about all they need to do with electricity. That was called the amber effect. Now, anyone know what amber is? It's basically fossilized tree sap. Okay? Like pine sap that you have, if it became fossilized, turned into a mineral, that was amber. Rub that with fur or something like that, wool or something like that, and what you're doing is rubbing charges off the fur onto the amber. Okay. That was the ancient mystery. No one knew why it happened. J.J. Thompson, and by the way, this chapter and the next chapter got tons of names in them. So if you haven't chosen a paper topic or write on somebody, there's going to be plenty of them here. J.J. Thompson identified these particles that we now call electrons. I don't know if he named them or not. They say negatively charged electrons. Actually, if I'm not mistaken, Benjamin Franklin was the guy who decided, well, let's make that let's just name them negative, which is sort of sad because that makes our whole field theory kind of backwards, okay? But we'll get there in a minute, okay, in a little while. Not tonight, but next time. So J.J. Thompson identified these negatively charged electrons. Now, basically what's going on here, well, here today, the basic unit of matter is the atom, okay? Now, that's of elements. For compounds, it would be a molecule, but we'll go down to the basic unit being an atom. Atoms are made up of three components. There are some other components that are in there, but the three main ones are, in two places, a nucleus, which is made up of protons and neutrons. Now, the nucleus is incredibly small, but all the mass is in that one little nucleus. The electron cloud is huge, but hardly any mass at all in there. In fact, the electrons themselves are about 1/10,000th the mass of either a proton or a neutron. I mean, just almost negligible compared. And yet, they take up most of the space where the nucleus, where all the mass is, takes up very little volume, but it's all the mass. So this is an incredibly dense nucleus. Now, the one they've drawn here for you, you don't need to know this, they just did a representative, this would be helium. Helium is made up of 2 protons and 2 neutrons. You don't need to know that for this purpose, so just showing you a nucleus. Tiny, tiny little nucleus, but it's extraordinarily massive and surrounded by electrons. Now, actually, around helium, you only have 2 electrons because you have to have the same number of electrons as you do protons. Those protons are positively charged, electrons are negatively charged. For this to be neutral, they have to be the same. Neutrons have no charge, so you can have extra or a deficit of neutrons. It doesn't matter. It matters to the stability of the atom, but it doesn't matter to the charge of the atom. So atoms are made up of electrons, very tiny little particles that float around, revolve, circulate around a nucleus. And the nuclei, which is incredibly tiny, but has all the mass pretty much in it, okay, containing positively charged protons and neutral neutrons. That's our model, okay? Now, we'll talk about this more in the next chapter, chapter 8. But we've run out of time, sorry. So we'll start with the electron charge, and that would be electron theory of charge right here. That's where we'll begin next time. Okay? All right. I'm going to pause the... All right. You had... Okay. As soon as... Okay. Now, don't get ahead of me. Okay? Once you get the mix of... Pour all the water from one cup into the other. And don't break any thermometers. Okay. Okay. Once you got the A part done, cups 1 and 2, pour them into 1 cup, take the temperature of that, that's your mix. When you've got that done, then remove the cups from 2 and 3 and 4, put your thermometers in those 2 cups, and measure the temperature of the water in those 2 cups. But don't mix them. Just measure the temperature. Okay? Everybody got the A and B done? Still working on it? Okay, C and D, don't mix C and D, just take the temperature of those 2 cups. Once you got the temperatures of them, then you tell me what your guess of the temperature mix will be. Make a guess, an estimate of what you think the temperature of the mix will be before you pour. Somebody got it? Yeah, do the estimate first. What you think? You see the cup temperature in cups 3 and 4. You estimate what the mix is going to be.
It's going to be about, our mix is going to be about 27, 28.
Okay, write it down. Okay? Everybody written down what you estimate the mix will be?
Yeah.
Okay, then pour it. Once you estimate it, then pour 3 into 4, 4 into 3, I don't care which. And measure the temperature of that mix. And don't break my thermometers, okay? All right. Have you estimated? All right. Have y'all poured and measured now? You estimated, poured, and measured. Did you find that A and C, on number A, cups 1 and 2 and 3 and 4, those temperatures were very close to each other?
Yeah.
A, cups 1 and 2 and 3 and 4, close? Did you find that the mix 1 and mix 2 were that close?
No.
No. So you tell me on number F, if the answers to A and C were close together, why are the answers in B and E so different?
Hold on. A and C, you talking about 1 and 2?
A, cups 1 and 2, C is 3 and 4. Okay. Cleverly disguised.
Tell you why.
Why?
Oh, wait, the answers of B and D aren't so different.
What's that?
The answers of B and D aren't so different.
They're not? Okay, well, that's 5 degrees different. Why are those further apart than?
Oh.
Yeah. Okay. Why do you think the answers for B and E are so different when A and C were fairly close? Okay? This
amount?
very good. What did you say?
The amount?
The amounts of water were different. If you notice, 1 and 2 were almost equal amount. 3 and 4, there was a lot less in 3 and more in 4. So you're not just averaging temperatures, you're measuring really heat. Okay? Now, we've only got 2 scales here. We got 5 teams. So move these things along fairly nicely. If someone will take an empty cup and put it on the scale, put it on the scale and then zero the scale. Okay? And once you've done yours, move out of the way for another team to do his. There. All right, I'm sorry, I didn't quite say that right. With it on the scale, wait. Okay, with that on the scale, before you do anything, I'm going to give you some water to put about half fill your cup. Don't use number 1, use this water. Special water. About half fill the cup. Okay? Zero the scale. Okay? Then fill about halfway. Halfway. Okay. And take the mass of that. Just anywhere close. Okay? Give me the cup back.
In what world?
Okay? Now, you got it? Okay. You got it? You got your measurement?
Mass of water.
Right. You got it?
What's the mass of water, Tom?
It looks like 325 grams.
0.001. Okay, then you can take this off the scale and make room for another team to come and do this. Okay? Take it off the scale. So another team can use the scale. You go and do what you're doing. Okay, another team use the scale. Yeah. Zero the scale, and then let me give you the special water they put in. You pour it all. Okay? Okay, not yet. Where was the scale of your backpack? Was this your water? No, this was one thing. I had another bit of water. Okay, was that the water I gave you?
Essential for business.
Okay, you didn't just pick it up and saw it here. Okay. No, not that water. That's why I said don't use any water except the water from this. Okay, that's one. You can't use your scale. Don't use the water. Okay, we're doing the other one here. Okay. I know, but that's not the water you use.
You got special water.
That's why I said don't use it. Okay? Fill it about half full. Fill it about half full. Come on, I'm going to cover it. Only about half full. You zero the scale?
What about half? Not the whole thing.
Okay. All 5 teams done the first part of this. Okay. All right. Get this. No. Okay. Okay. Zero the scale with your cup on there. Only about half. You fill it about half full?
Ours got tape on it.
About half full. Okay. Anything will do. Hand me the other one. Okay.
It's about 300.
Zero the scale?
312.
What's wrong with that? Okay. Okay. Is the scale free now? Have you done it? Have you measured the temperature of it? Okay. That's now. Okay, have you measured the temperature of it? Alright. Okay, clear the scale out, and the first teams that were there. Okay, did you measure the mass of it? Okay, yeah. Put your thermometer in and measure the temperature of it. Okay? Move out of the way so people can get to the scale. Move out of the way so other people can get to the scale. Okay? All right. Now, get another empty cup. Some teams that did the first one. Get an empty cup. You need to move on this one. Get an empty cup. Put it on the scale. Zero the scale again.
312?
Yeah.
No, 312.
312. Now, what you do now, I've lost my. Okay, there's a lab lying around somewhere that was mine. It's blank. Does anyone see it? No, here. You got it. Okay, thanks. All right. This time. It says put a few cubes. What I want you to do, about how much was your mass of the water you just did? Okay. I would say put about 20 grams of ice into the one that you have on the scale now. Okay? So you might have to just do it with your hands. I don't have to scoop. Yeah, just put a little good. Don't break it much. Okay. Yeah, just do that. Okay, see how much that is. How much is it? Okay, that may be, okay. Try to get a little less, you got too much. Just do a scoop a little with your hand. Yeah, that's fine, you can do that. A little bit more. Okay. Just something other. Okay. All right. Get it off the scale. Put it in the water. Your hot water that you have, wherever that hot water is. You want your hot water. Yeah. Put it in your hot water that you have your thermometer in. Okay. Get out the way so another team can come. Get out of the way. Okay. And cover it. Take this out and cover it.
After the cup is on there.
Put it in there.
Put the ice water.
Yeah. Take the thermometer out. Put it out and put the cup over the top. Cup over the top. Yeah. All right, that's zero. You got it? Okay. Here's that for you.
That is 3 ones.
That's fine. Go for it, fine. No, that's fine. What you got? That's fine. A little over 20. You're fine. That's good. Okay. Clear out the way. Pour your ice into your hot water. Whatever you did with your hot water, pour it into it.
Let's find out hot water. Hold on.
Okay. Pour it into your hot water. And cover it. Take the thermometer out and cover it.
Okay.
Take it out. Wait. Take it. Where's the one? It's not this one. Okay. Take the thermometer out and cover it. You got your ice in there, right? Where ice is? Yeah. You got it? Okay. Oh, you need the ice. Water.
I'd say it's around 7. Then I don't work
All right. For the ice and cover. As long as it's melted. Oh, okay. Once it's melted, check it periodically and see if it's melted. But don't leave it uncovered for long. Okay, I left my lab somewhere again. All right. After a while, you uncover and check and see if all the ice is melted. See if there's ice in it, boy. Still ice? Okay. Okay. If it's still ice, then here's what you do next. Cover it. Leave it covered. But if there's still ice. No ice? Okay, measure the temperature of it. Once all the ice is melted, measure the temperature. I'll pay attention. Okay. Okay.
Yeah. Let's see if there's ice in that thing.
What is the equation?
The ice in it?
Is there any ice still in it? Okay. Has everybody completed their measurements now?
Sir.
All teams. Let me know if you have not. Every team has. Good? All right. Okay. So everyone's filled out under part 2. You filled out A, B, C, D, and E. No, D through D, right? Everybody got through D. Okay, so everybody should be on the same one now on number E, right? Write the equation to determine the heat loss of the original water that was back here in the A, the heat loss for the original water, and then determine that heat loss. What's the equation? You tell me.
So,
Say again?
NG, NC at
Okay.
delta T.
Okay, what is that?
Q
Q, and let's call it QL,
equals
is equal to, what you say?
mass
M,
C
C,
at delta T.
delta T. Okay, now what's your mass here?
That would be 32
Whatever your answer to number A was, right? That's the mass of the water you're talking about, right? Yeah, look back on the first page, 2A, calorimeter, mass of water. That's your mass here, right? What's your C?
the temperature of the water.
No. What is C? We went over this.
Mass of the water.
No, M was mass of the water. What is C?
Oh, the Celsius would be
No, it's not Celsius. What is C? Little c. Specific heat. Very good. And what is the specific heat of water?
40. Temperature of water.
What is the specific heat of water?
20.
What is the specific heat of water? We went over this over and over in
1
class.
calorie.
1 calorie per gram degree Celsius. So your mass was some sort of number. Each team has a different one in grams. The C is 1.00 calories per gram degree Celsius. Remember, that's your C. Okay? What's your delta T?
The temperature of water.
The temperature of the water? What does delta mean? Change of temperature of the water. So that's the difference between your B answer and your D answer. Right?
So average those two.
No, you difference of them. Subtract. The little one from the big one. Say again? Okay? 2B, or not, and 2D. The difference between those two temperatures. Right?
So just 26 and 23.
Whatever you happen to be. And that will be some number in degrees Celsius. So the grams are going to cancel out, degrees Celsius cancels out. That's going to give you some number of calories, right?
Yes.
Okay? You see where you have temperatures. Isn't B a temperature? On the first page, at the bottom of the page, isn't that a temperature? And then on the next page, D, isn't that a temperature? The difference in those two temperatures is your delta T. Delta means different, delta T.
But D and D is not heat loss, right?
What's that?
Is D minus D the heat loss?
No, that's a temperature change. The heat loss you get from the formula. The delta T is the difference in the two temperatures. The B temperature and the D temperature. The difference between those, that's your delta T. That's what goes here. That's sounds three. That's in three. And what's that measure? Calories, exactly. Okay? What's that? Do you have a number?
Yes.
Okay, let me see what your number is. I'll tell you if it's reasonable or not. That was reasonable.
Okay.
You got a number? What? What's two? Now you show me where you got a two. No, where you got the two.
The second box.
So
try to do B from D. B from D, that B up here, this B.
what is that?
B and D on this.
40.
Qualify that as common qualifying.
The difference between those two. Difference in temperature. Yeah. Don't go back to the first experiment. That's different water, different everything. This experiment. Okay? Don't be pressed. Okay, has everybody got a number?
What about 750?
That's a little low, it sounds like. How did you get that?
You want to find the 30 times.
The mass of water is only 30 grams. I think that's not. Okay? Okay.
That wouldn't have.
Come here. Come here. Come here. Come here. Fill that to about what you had before. This is not the same water.
Actually, it was
330, or yeah, if it was 30 was right, it's 330. Okay?
My bad.
All right. Has everybody got a number?
No, 3.
For E?
Yeah.
Okay. You got it? Yeah, I already seen yours. Okay. Yeah. Okay, what's this?
I don't know none of this means right here. What you want me to do in the future? What is it?
And that's the heat loss formula. The mass of water, specific heat of water, and the temperature of water. The mass of water is all that. What's the mass of water?
The mass of water is.
Yeah.
3,000 grams per kilogram.
Said yeah, it is. You're acting like stupid.
What's your C?
He did.
Let's see.
No, we got the,
No.
No, she is 47.
No.
The mass of water,
23.
No.
mass
I wrote it on the board.
of water.
But you said the laws of the water.
No, I said the mass of the C. What is C? Look at the board.
I can't understand what's on the board. What?
Isn't that the same formula you have?
Yep.
Okay? The mass is the ground.
Yep.
You see the C?
So it's 100.
No.
1.
What? Okay.
1.
One what?
Grams.
No.
Calorie grams.
Calorie per gram degree Celsius.
22.
Okay.
And then times the loss of the heat.
No. Delta T. What's your delta T?
It's the loss.
What's the delta T? Delta means difference.
Difference of
T stands for temperature. What's the difference in temperature?
on which one? This one?
Okay. We are through with that part. We're doing the calorimeter. Okay. 40 degrees was the original.
Yeah.
What's the final? Okay, there's the difference. What's the difference? 18. You got it.
How about that?
Yeah. Okay. How are y'all doing? Here, you get a number yet?
What you doing, man?
What was y'all's answer? Y'all got it? I don't hear it. Could be.
1 calorie
I
per
was
gram.
curious out there, was it 40?
So we don't have that.
His facial expression.
5,000. Sunshine will. Let me call Sunshine. Hold it up.
Dude, call him, bro. That's what he does.
What is that?
It's the guy he was talking to when he said that.
Look at the board. If you look at the board, you see it? This is the mass was in grams, and this is in calories per gram degree Celsius. The grams go out.
And the
This
cells
is
go
degree
out.
Celsius, the change in temperature. This is calories per gram degree Celsius, and degree Celsius goes out. What you got left? Calories. That's heat measured in calories. Okay? Everybody got a number? Y'all have a number yet? What is it? Okay. Now, finally, we're ready. Everybody got a number, and I said it looks reasonable, right?
Yes.
Okay, the second part, the F. Write the equation to determine the heat gained by the melting ice, and then we'll calculate the heat gained by the melting ice. What equation do we use to melt ice? Q, G, melting. What is our formula for melting ice? Okay. We had it in class, and I said we're going to do it again in lab.
Oh, it's up to.
When you melt ice, what are you changing?
Temperature.
Temperature? No.
Oh,
Phases.
Phases. So there's no change of temperature. So what is the formula? If you have no change of temperature, then you don't use specific heat because that has a change of temperature in it. You lose what other kind of heat? You use it. It means hidden heat. Latent heat. Okay? So that would be L is the latent heat of fusion, which is the same as freezing or melting, times the mass. You can put the mass in front or behind, it doesn't matter. Now, what was the latent heat of fusion for water? We went over this in the lab several times.
You wasn't there. You didn't get there after we were done.
You can do the mass of ice.
Okay, the mass of the ice. You're absolutely right. This is the mass of the ice, not the mass of the water. Okay? What's the latent heat of fusion? What's the latent heat of fusion?
Is that a backwards J?
Where?
That's M.
Mass of the ice. That's what
That's a J.
absolutely. 80.0, what was the unit?
Calories per gram.
Calories per gram. And we're multiplying that by what? What we're multiplying it by? Mass of the ice. Whatever your mass of ice was in grams. And again, the grams cancel out, and you're left with calories. Right? So there's no change in temperature here. When you get a number, let me know. Looks reasonable. You got a number, let me know.
So it's going to be 8 times.
No, it's not an 8.
That's an 80.
80.
You marked out the zeros.
Okay, I slashed my zeros. I've been doing it all term. Okay. Oh! You tried me there. Caught me by surprise. Oh.
Is 27, 22.
This is not going to hurt.
Yeah, that sounds reasonable.
Let's do it.
Mass of ice. Mass of ice.
Thank you.
Okay. What you get, I said. Oh, that sounds Whoa! Whoa!
8600.
Did it all melt? Before you... Y'all wrong. Y'all wrong. Calculate. Everybody else.
How much ice y'all had?
That's a lot.
How much is this?
I don't know what's happening to yours. Is this it? Or
Exactly.
Yeah,
What
what
is
is
that?
that? Okay.
The answer's 5,600 others, guys. I figured that out on my own. Y'all ain't know that. 5,600.
Yeah.
56.
I'm wondering if y'all didn't have 430, not 330 of water. Oh, wow.
I keep pulling in right behind it.
We'll live with it. Okay. Now, all right. Number G. G. Write the equation to determine the heat gained by the melted ice water. So this is the QG by the melted ice. Okay? It's water now, but it was melted ice. So what is the heat gained by that? It's now water. It's no longer ice, it's water. Now what does that temperature be if all you did was melt the ice here? What would be the temperature of the ice? 0. And then it went up to 30, whatever your D was. Okay? And what would be the formula you use for that? You're changing the temperature. So what formula do you use?
You already said I was going to answer.
Second?
You already said he knows the answer.
I can't hear you.
You already said
Oh.
he already said
Okay. What is the formula you use for changing temperature?
LP.
That has no change of temperature, no delta T there.
The MC.
MC delta T. Okay? Now what's your M?
21. Mass of ice.
Mass of the ice. This is mass of the ice, not the mass of the water. Mass of the ice. Because that was your melted ice. What would you see?
Cal. 1 cal.
1. Yeah, 1.00 calories for what?
Grams.
Grams, degrees Celsius. The grams are going to cancel out. And what's your delta temperature here?
32.
Second?
The temperature of the ice water.
Yes. It went from 0 to that, so whatever your temperature of the ice water was. That's your delta T in degrees Celsius. And degrees Celsius will go out. Multiply those together and see what you get. Okay, the difference between here and here, this is the mass of the water, this is the mass of the ice. Also a change of temperature here. This was the temperature of water cooling, this is the temperature of the ice warming. So those are different temperatures.
The M with 0.
The what? The what? That's reasonable. Okay?
So, 950. The delta T would be the same.
Same as what? It's going from 0 because you're warming the ice pot. So it went from 0 to there's what ice pot.
Go to the next three options.
So this one's 21 mass of ice.
Okay, yeah, just put grams. So it's mass.
Still would be showing
Yeah, that's your 32.
Do what?
That's the mass of ice is in grams. You clear the units?
What was you doing?
That's easy. Okay, does everybody have a G number? You got a G number yet? What you got?
I said 1540.
Second?
I said 1540.
I know the answer. What number?
We had too much ice, remember? Remember I had a whole bunch of
I
ice.
kept asking you, did it all melt?
It all melted, yeah.
You did? All right. Okay. It's okay, I can't really tell you about it. This calories. You got any G number yet? Got a G number yet?
We have G and H.
I'm here to wear it in the shower.
Okay. Now, everybody, all the teams got a G number, right?
Yeah.
Okay, you add the F number with the G number to get your total heat gain. Has everybody done that?
Yes.
Okay. Now, just as a general thing, is that fairly close to your E number?
Yes.
It
Yes.
should be. Okay? So what I want you to do next is subtract the smaller from the larger between the E number and the H number. What difference do you have? Should be fairly small, right?
32.
Oh, you're kidding me. Look at that. Excellent.
168.
Okay, that sounds reasonable.
So, for the answer why, I mean, like, when you say why, mine's the largest one is the total heat gain, is that the item?
Here's what my guess is for you.
Is that car running through yet?
Okay. On number I, the difference is the difference between the heat loss number, E number, and the H number. Everybody understand? I'm going to be here till 8. That doesn't bother me any. Okay? Okay. Everybody got the difference there. The difference between E and H.
Yes.
Okay. Now, when it says which is larger, okay, that means you answer either gain or loss, not yes or no. Oh, did you get one of these?
Nice to meet that class.
You have to get one of the things that goes to that. That's either this thing or that thing.
You know, Chelsea's time now. Birds me. Yeah, birds.
I almost feel like giving somebody a bird. Okay. I recorded that. Okay. All right.
Birds.
Okay. You got an answer? Okay. Now, the question is, okay, you tell me which one was larger, the gain or the loss? The gain. You gain.
Wait, what?
Tell me what your temperature of the final ice water was. 15 degrees Celsius. Would you say that 15? Yes.
Our loss was greater than the gain.
Okay. What was your temperature of the ice water?
28 degrees.
Okay. That's higher than room temperature, right? So you lost some heat from that to there. You uncovered it, right? Yours was way below room temperature. So you gained from that. So that makes sense. Y'all got answers?
Why are you inappropriately parsing the skeleton?
He did it. Blame it on him.
What do you do? What do you do? You can put anything in there. You tell me. I'm watching it right now. Put the skeleton all over her, but he did it.
Okay, everybody got those answers done.
It's his fault. But she has the skeleton hand in her hand. Okay. All right, so we on 5 now.
Well, that's 4. Okay. Does everybody have the 3 I's answered?
No.
The difference?
I do.
I told you what they were.
You didn't say
I
why.
did too.
No,
Because we had a lot.
you got cut off.
Cause it wanna be.
You didn't give the run
That
off.
why? You have to set it game straight. What? Okay. Why? Look.
I don't think Sheshan's gonna make this stuff up.
Well, 20 degrees Celsius.
Bro, you got one too.
So 5, 6, 16. So you gain 40. You get 15 because difference in the room is greater. You gain 16. And my guess is you probably uncovered it before the ice completely melted. All that 110 grams of ice was melted. And this session is like that.
I don't get it.
Does he know Candace?
I don't get it.
I'm just there.
Okay. On yours? Okay. 32 degrees different. I mean, calories different. That's in calories, by the way. That's all these are in calories. Okay. Now, that's so close, it really doesn't matter. Okay. You're so close. You got 32 calories out of 2,000 calories. That's negligible. Back to that. Put that in your calculator. 32 divided by 2352.
What does that say?
Okay, That's less than one, just over 1%. That, okay.
So what were we
You're so close. You did your experiment. There, you're within 1%. You're within 15%. You're within 2%. Oh yeah. Okay. Has everybody finished group I?
Yes.
Yay? Okay. Now, I have over here, close as I can get to the thermometer, some pieces of aluminum and some pieces of plastic. Okay, what I'd like everybody to do is to take a piece of aluminum and a piece of plastic. Well, first thing you do on conduction in number A, find a metal and a plastic object on the bench right there. Since they have been exposed to the air in here for hours, what do you think your temperatures are?
Room temperature.
Room temperature. 71 degrees Fahrenheit. Now hold one, you keep it here. Hold one to each cheek. No, flat one. Yeah, that way. Okay. Which feels colder or warmer? Which feels
Plastic.
Okay. Which feels warmer?
The plastic.
Plastic feels warmer.
Put it in your
But
mouth,
you
Jerry.
know they're at the same temperature,
Yes.
right?
This one.
Huh?
This is the same
What's
thing.
going on? Yeah. Yeah, exactly. Let somebody else do it.
Which one, Andrew?
Would you like to attempt this?
Huh?
Okay.
Aluminum.
Okay.
What do you think the estimated
Go
temperature
back to
is?
where they were. Okay.
What do you think the temperature in the middle is, Jerry?
I put down 6 degrees Fahrenheit.
Wait. What was the temperature of the room? Read it off the thermometer. 71 degrees. That's going to be the temperature of both the metal and the plastic. Right? Oh, thank you. Correct? They've been sitting in the room, they're at room temperature. Right? Okay. But why does they feel different in temperature?
Because one of them contains.
Read number C.
Because the plastic has less
Conductivity. Exactly. Okay. What you're feeling, if you put those against the cheek, a facial cheek, okay, what you're feeling then, with the metal, it's conducting your heat away from you, you're feeling 71 degrees. The plastic is not conducting the heat away, so you're feeling something pretty close to 98.6. I'd say about 90 degrees. So what you're sensing is your temperature with the plastic, the room temperature with the metal. Because the metal conducts the heat away, the plastic does not. Okay? Good deal. Thank you. All right, y'all have a great Thanksgiving.
You too, man.
everybody. Enjoy your week off. Get your papers written. Okay?
Don't yell at me.
All right, good deal. Thank you. Did you find the lab instructive? Did you find the lab instructive?
Always.
Always. Good. Getting a good answer anyway. Have a great weekend. Week. Good deal. Thank you. Good deal. Pretty exciting stuff, huh?
Yeah, I wasn't here for any of it.
Okay. Did you get
I did.
what was going on?
What was the first experiment?
Had water in the cups, and 2 cups. 1 cup was 30 degrees Celsius. Okay. Yeah. Yeah. Watch out for cutting your feet. Huh? Okay. Degrees Celsius. That's it. So there were 2 different temperatures. You poured them together and it came out somewhere in between. All right. These were fairly close to the same temperatures, right? Of course, you estimated, or he estimated, somebody estimated they'd be the same, quite a bit cooler. Now, the difference there was that you had
almost the same amount of water in these two cups. You have a lot more cold water in this cup and less hot water. So you don't just have a temperature, you're actually measuring average kinetic energy. So that's what that was about. And then the next one was using the heat flow. Specifically like we did the class. Do you remember for that one? Yeah. So it's almost the same like thing on it. It wasn't refrigerating one. But yeah. All right. One. Good deal. Thank you. Have a great Thanksgiving week. Thank you. Appreciate it.
Get some rest.
That's right. My wife will probably work me to death. Okay.
About that. My stepdad worked me to death.
What's that?
My stepdad worked me to death.
Someone left a pen in here. I wonder if it's.
Don't worry about it. I want to do my paper on something around drag race, but I can't figure out what I should do, like what index revolves around physical science.
You could maybe even talk about, look at that, it was in the ice water and it was right at 0 degrees. But calibration of that thermometer must be all right. You could talk about the kinetic energy, because you're going from 0 to pretty high speed. Yeah. And you can talk about that, perhaps. Or you, in fact, I would look it up, say online somewhere, and see, do physics of drag racing. I bet you can find something that.
You said 1 page long, right?
1 to 2 pages.
What all would you like to be in it?
Like a little bit of physics in there, and if you find some chemistry, you can do that too. You can talk about what the drag races, do they still use parachutes to stop?
Yes, sir.
They do, okay.
If
And
you're
you
going
talk
to
about that. I mean, that's providing air resistance, and that's what you're using to stop with. So there's really a lot of physics in there.
It's just a matter of
You pick out and follow and which you're more interested in and work on that. But I would say go to Google or any other search engine and do a search on something like physics of drag racing or something like that. But not all of them fit all that well. I'm going to throw some off the plate too. Got a little more than I need.
they all cut out, didn't they?
What's that?
They all cut out, didn't they?
I think so. Thank you for helping.
You don't want to be here as much as we don't want to be here.
Hey, I stay till 8 anyway. So it doesn't bother me. But it gives me a chance to get a few more graded. So
I just want to ask you about that because I really didn't know where to start at. I tried to look up some databases, but I wasn't really pulling up anything.
Yeah. Did you do a Google search or something like that on physics of drag racing?
I did, but
You didn't get anything?
I didn't get anything behind to go in more in depth to it.
Okay. Like I said, you could talk about the energies involved, and I mean, you could even get into the.
Could I do it on multiple things, like the kinetic energy and
Yeah,
all that?
right.
And the amount of force it's taking to stop it.
Yeah, absolutely. All those are great topics there. The energies, the forces, the friction, air resistance.
Do I need to have any like numbers or anything in that, or do I just need to talk about it?
Well,
Because
as long as you're talking about some of the physics aspect or chemistry,
Because it's kind of hard to get some numbers on that.
Yeah,
There's not really
it may be.
anything out there.
yeah, if you can just talk about it in terms of the science terms, physics, chemistry, forces, energies, resistance, friction. Because when you start off, do your tires spin like crazy?
Well, you go burn out and then
Yeah.
you back up and then
you stage and you're holding, you use a foot brake or you have a trans brake, which you're building up potential energy from the engine, and when you let off, it's going to gain a lot of kinetic energy very fast.
And you're talking about impulse, so you could get that. You change the momentum over the time period. Impulse, you could get that into it. Man, you're going to have a hard time getting less than 2 pages. But just pick and choose, Where you can talk about impulse, energy, forces, resistance.
You want these like double spaced or
double spaced?
Double spaced.
Yeah. So 1 to 2 pages is not going to be hard with as much as you've got to talk about there.
I just got to figure out how to work.
Yeah, exactly. But you need some sources. So you need to, that's why I say you really need to find something. Yeah. And there are so many things out there that people have tried to get applied stuff for, and I would almost be surprised if you can't find something. And it may not be drag racing, it may be racing in general, But drag racing, don't talk about the curves because you don't have any curves in drag racing.
Yeah, you turn, you're going to
be
have a bad day.
Yeah, a very bad day. So yeah, that sounds reasonable. And like I said, the forces, the energies, the momentum, and resistance, all that is involved in some place or another.
Maybe I could calculate. I got some friends that have drag cars, and maybe if I can get the weight of the car, how the time they run, and how much horsepower they got, maybe I can do some calculations too.
Right? Yeah, possibly so. But you need at least one outside source, so it can't just be stuff you're making up. But find something. Look under.
They have to be documents.
Yeah, something you can do.
So 1 or 2 sources.
One is sufficient. But if you find 2 or more, that's even better. But at least one. And then the rest of it can be stuff that you've done, talked about. But
because over this Thanksgiving break, I'm going to be working, and I'm going to be trying to catch up because I know I missed a lot.
Yeah, I think yours is one of the first layouts I'm missing, right?
I know. I got to figure out how I'm going to do that.
Which reminds me, I need to shut this off. I'm recording.